Very good morning. So today we will be doing activation functions which are commonly used in neural networks. Although we covered the activation functions in the basics of neural network, we covered that why activation functions are useful. So in this lecture we would be only focusing on the activation functions which are commonly used for neural networks. Now, as we all will just do a quick recap on why the activation functions are actually required. As we all know that in the basic model of a neuron, we every neuron basically collects what? It basically collects this weighted sum, that is the product of your input and the corresponding weights, right? And along with the bias value if it exists. Now, this summation, once it is collected at every neuron, now we have to make sure, or we have to decide that what has to be done with this collected input. And that is where the role of activation function comes into picture. So this activation function would actually decide that what has to be done with this received input. So normally we do two things. Either we can inhibit, or either we can stop the neuron from being fired, or either we can decide that we are going to fire the neuron. So firing of the neuron is one aspect, and stopping firing of the neuron ultimately means that passing this collected input, or passing this input after some kind of normalization applied on this input, we can pass it to the further layers or to the further neurons. So in case if we decide that what has to be done with this collected input, we have to write a function which basically takes this input and produces some kind of specific output. Now, if it is simply a linear function, then it would be basically the output classes would be basically a binary. Either it would be yes or no, either it can be 1 or 0. But that would limit the functionality of the overall neural model, overall neural network, because dealing only in terms of linear function is not going to give us much of the opportunity to learn from the neural model. And that is where we need to look other than the linear combination, and that is where the activation functions, we say that the major purpose of activation function is to learn the non-linear functions from the model. So this function f can be both linear as well as it can be both. It can also be non-linear functions, right? So we will talking about some of the very common non-linear functions that are being used in the literature. As you can see over here, so the function can have a linear nature where it only by putting a separating line or a linear line, it is able to classify the two given inputs when defined in a 2D plane. Whereas if you see at the right hand side of this diagram, you would find that in this case, it is not possible to draw a linear line and classify the two kinds of inputs, that is green and blue circles. So in that case, definitely we have to look upon beyond your linear functions, and there that is where the role of non-linear function comes into picture. So as far the definition or the basic difference between the linear and non-linear function is concerned, so if you say that if the output values have a difference that is constant, then the function can be classified as a linear equation, right? And if you're not able to do so, then if it is not a constant and is dependent on the, however, if the output is not a constant and difference will be classified as what? This can be classified as a non-linear equation. So we'll be majorly covering the non-linear functions. The non-linear activation functions are the most used in activation functions. This, if we try to understand more on why a linear regression model or linear model is not good enough, because if we only consider the linear combination of your inputs and the weights, which we do in terms of collecting the total input, which we call it as a total activation input, then it will have a very limiting kind of power, a very limiting kind of factor, which cannot perform most of the basic tasks also. Like for example, if I have to classify or if I have to learn the functions of XOR, even for two inputs, then with a simple linear model, we would not be able to do so, right? So if in case we want our network to do something significant, not just learn a linear combination of inputs, then we have to complicate the things. We have to use the nonlinear functions. And very obviously, without these activation functions, the neural network would be only able to learn and model the other complicated kinds of data. Like, for example, with linear combination of learning, we cannot classify, or we cannot do learn the complicated data such as images, videos, audio, speeches. And therefore, we are talking about these nonlinear functions. The activation function, if we just put everything in a summary, these activation functions does the nonlinear transformation to the input and just making it to learn and perform some complex tasks, right? So that is what is the basic purpose of your activation functions. We have all done this linear function. As you all know, linear functions, that is y is the output, and x is the input, right? And a is some constant. So it would be of this particular nature, right? And the range can be from minus to plus of infinity. And as I've already told, basically it is used for binary classification kind of task, where it is used just for one place, that is at the output layer. And the issues we have already discussed, that if one of the primary issues with linear function is that because when we would be talking about the continuous function, then these functions would need to be differentiable, right, at some point x or some input. So, but these linear functions would not be differentiable, and therefore the result will not will no more depend on your input x. It would become a constant, and the function will become definitely a constant. So definitely it won't introduce any major groundbreaking behavior to our algorithms. You will not be able to learn anything significant other than just a binary classification. So that is one of the main issues, because these functions are not differentiable, and that is why the linear functions are not used as much. So we'll take the examples of nonlinear functions. So we actually define it as like the nonlinear functions are those which have more than a degree more than one, and they have a curvature that curvature when we plot a nonlinear function, right? So we'll have always nonlinear functions will always a degree more than one, and it would be almost you'll see a kind of curvature, not a single or straight line. And we need a network model to learn definitely the complex functions, and which can map to the inputs to the output, because you cannot find always linear combination or linear mapping between input and outputs. So neural networks are considered as you all know, the neural networks are considered as what? The universal function approximator. That means to give any input and output and ask it to produce a function. So it can learn any input and can map any input to the output. That is the reason why it is called universal function approximators. Provided there is enough amount of training and the right amount of training which is being carried out. So it is actually considered to be a universal function approximator. And definitely such nonlinear functions, as I've already covered, that it should be differentiable so that we can perform some kind of error calculation at the output unit, and then we can back propagate, or we can somehow decide that what has to be done with that error. Those errors can then be optimized. For example, in the case of back propagation, we used to send those errors back to the different layers by using a gradient descent method. So these functions, nonlinear functions, have to be definitely somehow differentiable at some points in the domain defined by the function. Now, one of the most common activation functions that we have already done and we have been using it is the sigmoid or the logistic function. Now, the sigmoid function basically, as you all know, looks or produces a S curve, right? And the value which it can produce for any given input, it can convert that input into a range of what? 0 to 1. We all have done that, right? And definitely this function is differentiable, right? So what it means that we can definitely find the slope of the sigmoid curve at any two given points. And the logistic sigmoid function can cause this neural network to stuck at a local minima, which is one of the disadvantages of logistic function. As we have already done in the previous lectures also, that there is a problem called local minima. That is, for example, if we are making a neural network to learn, and after some time we may decide or we may come to a conclusion that yes, my learning is complete, but that decision may be wrong, because we may have stuck into a local minima, and we may have assumed that we have got the right amount of convergence, but which may not be true, because if we run the further iterations, and so we may find that the error comes down further also. So rather than reaching out to the global minima, we declare one of the minima as a local minima and declare it as the perfect solution, or we declare it as the convergence, which is wrong, or which is not true for the learning parameters. So this logistic function, sigmoid function, can have a possibility that can stuck into your local minima at the time of training. So that is what is one of the disadvantages of your sigmoid function. In order to overcome this function, there is a variation of sigmoid function, which we call it as a softmax function, which is a more kind of generalized logistic activation function. And moreover, the sigmoid function can only be used, or most of the times we does not use it for multi-class classification, but softmax functions can be used for multi-class classification as well. So we'll be learning about softmax functions in this upcoming slides. So this sigmoid function, as you all know, has nature of this form, where we have x as the input, and then we take what 1 upon 1 plus of p raised to the power of minus of x. So this would always put or will create a values in the range of 0 and 1, as we have already seen, and we have been using it in a number of places. For example, in vector position learning. Now, besides like being a very commonly used function, it has a drawback also. Like major sigmoid functions have a range of values from 0 to 1. So this also actually means that the sigmoid function will not be symmetric around the origin, right? And the values received are all positive. So as far as the values are near to 1 or positive values, it is doing fairly well. But it is the only problem when the values are negative. So we are not able to center the inputs or center the errors at the point of origin. So they are not symmetric around the origin, and that is one of the disadvantages of using the sigmoid function. So sigmoid functions, we can say that these sigmoid functions actually saturate and kill the gradients. Like for example, over here you can see that the activation of the neurons saturate either at your point 0, or either it can saturate at the values 1. So as far as the values are between this range, it works fine. But the moment it comes near to 0, or the moment it comes to 1, the values start saturating, and the derivative of the sigmoid function gets very small for these blue areas, that is the values which are near to 1, or either values which are close to 0. So once we'll take the derivative of these values, so howsoever is the big value of near to 1, or howsoever the small value near to 0, the derivative would become very small. In a simple sense, we say that the sigmoid function causes a problem called the vanishing gradient. Now, which occurs when we convert the large input into a range between 0 and 1, and therefore when we take the derivative, becomes very small, and which does not actually give any satisfactory output. Now, in order to solve this vanishing gradient problem, we have another function which is one of the most common activation functions for specifically for neural networks, that is called RELU function, rectified linear units, which will be covered in short while. So this RELU is used when we do not have a small derivative problem. It does not suffer from this specific problem that we're talking about, that is the vanishing gradient problem. And moreover, the sigmoid functions have been experimentally found that they have a very slow convergence. It takes a lot of iterations in order to reach to the convergence, right? And moreover, these sigmoid functions, as we have already told, it is not centered. It is non-zero centered. So, for example, if we consider this simple activation input, where we know that this is input, these are corresponding weights. This is input, this is a corresponding weight. So often this optimal gradient descent step requires what we most of the time we would require, like we have to increase the value of W1. On the other hand, we may have to decrease the value of W2. And since both this X1 X2 are always positive, the inputs are always positive, then we can not increase and decrease the weights at the same time. That is one of the major disadvantages of using sigmoid functions, right? So because we may have to increase the values of W1, and at the same time we may have to decrease the value of W2 in order to minimize the error, or in order to use this function. So this would not help us. So in the end, it will require more number of steps, because we have to find the right mixture of the right fitment of W and W2, so that we can reach out to the correct learning. So this is one of the major disadvantages of the sigmoid functions. Now, another function that is being used in neural networks is your Tanh function. Now, Tanh function, the zero-centered problem that was there in your logistic function, that problem is actually removed from here. So this range of Tanh function is in fact not from 0 to 1. Now it is from -1 to 1, and the shape would remain same. As you can see, the shape of the function is again the same thing. The sigmoid function has the range from 0 to 1, and here the range becomes from -1 to 1. So we are increasing the range. But still, this function also again suffers from the vanishing gradient problem, the way we discussed in the previous slide. This is how the Tanh function is defined, and this is the actual formula that we use for Tanh function, right? And one of the major advantages of using the tangent hyperbolic function is that the values of Tanh functions are zero-centered, which was missing in your sigmoid function. So, which would definitely help the next neuron during the propagation. So, this is one of the major advantages of the Tanh function. Now, again, the function Tanh function has the same problem, that is the vanishing gradient descent problem that we saw in the case of sigmoid function, right? And with the sigmoid function, the neurons saturate for large negative and positive values, and the derivative of the function goes to 0. So again, the same problem that we discussed. So both, unlike the sigmoid, its output are zero-centered. And therefore, in practice, the Tanh is non-linearity is always preferred to the sigmoid non-linearity. So if we have to take a non-linear function similar to sigmoid, so we would prefer Tanh function as compared to your sigmoid function. Now, the most popular function, activation function that is being used in the literature, that is the RELU function, the rectified linear unit, which is the most widely used activation function. And it is chiefly implemented majorly in your hidden layers of the neural network. So we at the input and output, we do use normal functions. For example, at the input, we normally use your sigmoid function, but for the hidden layers, we normally use your RELU function. At the output layer, we normally use, or the output, we normally use a softmax function or some other combination of such functions. But for the hidden layer, RELU is one of the most popular function that we use. Now, the equation of RELU is pretty simple, like AX, where X is the input. So it can result in the value of 0 or the X value itself. So it gives the value X if X is positive. So if this value of X is positive, it is going to give the value itself. Or otherwise, it will give you a value of 0, right? So the range becomes from where? 0 to infinity. So the nature is definitely what? The non-linear nature. Which also means that we can easily backpropagate the errors as required, with most of the activation, with most of the neural networks. And we have multiple layers of neurons being activated by the RELU function. See, if you recall, while using the activation functions like Sigmoid, one of the basic issues was that in the hidden layers we have to use each and every weight. We have to, in other ways, we have to decide upon whether what has to be done with. We have to take into consideration the firing of each and every neuron. But that makes the things a little complex also. So in RELU function, we can have like some of the units, only some of the units in the hidden layers would be in the activation mode or would be in the firing mode. The rest of the neurons would can remain in the inhibited mode. So this kind of facility was not present with your sigmoid function or the Tanh functions. So RELU is less computationally expensive as compared to the counterparts Tanh and Sigmoid, because it only involves simple mathematical operations. And the most important line is that at any particular point of time, only the few neurons are activated, making the network sparse and definitely making the network more effective and computationally less intensive, and therefore it becomes more efficient and more easier to handle, and the computations also become less. So that is one of the major issues or the major advantages with your RELU function. So performance-wise, these functions are pretty okay. So this is how the RELU function might look. And RELU function, let me tell you, it is one of the most commonly used functions for convolutional neural network and the deep learning. Now, RELU is, we also call RELU to be half rectified, that is from bottom. That is fz, that is function is 0 when z is less than 0, right? And otherwise, fz is equal to z. So when z is above or equal to 0. Now, this also creates some issue. If we use this RELU function in the same manner, then as far as the positive values are considered, these RELU functions doing pretty well. But the only issue is when we have negative values or when we have 0 values, and that is at point of time we are not able to map the inputs efficiently, right? So we have to find some other way so that this RELU function can be improved or optimized. The function and the derivative both are monotonic, isn't it? Over here, if we use the generalized form of a RELU function. But the issue is that all the negative values become 0 immediately because we have only two cases of outputs. One is 0, another is the value itself, right? So it becomes 0 immediately, which decreases the ability of the model to fit or train for the data properly. Because in data we would always have a mix of values. We would have 0, we would have your negative values as well. So as far as the values are positive, then it works fine. But if we have negative values, then then that is where the RELU function is not very effective. So there are certain variations of RELU functions that we can always use. So it also means that any negative input given to the RELU activation functions turns the value into 0 immediately and the graph, and which in turn affects the resulting graph by not mapping the negative values appropriately. That means simple, the negative values doesn't have a proper representation and does not have a proper mapping with respect to your output. So there is a variation of RELU function, which is, we call it as a leaky RELU, right? Now in the leaky RELU, we attempt to fix the dying RELU. That is dying in the sense because all the values, negative values were dying because it was ultimately we were producing the value 0. So we were killing the effect of those negative values, which may represent a very significant variance in the data. So instead of function being 0, what we can do is we can wherever we find the value x less than 0. So leaky RELU will do what? It would make a small negative slope. It will give you or provide a small negative slope, as it can be seen over here, isn't it? So this actually helps in giving some kind of significance to your negative values also. And we normally take this value of this slope, negative slope value of 0.01. So if this leak is going to, we will call this a leak, helps to increase the range of the RELU function. And this value of leak, or this value of constant is normally, as I've told, is in the range of what? 0 to 0.01, and so on. If in case this value is not 0.01, we start calling it a randomized RELU. So there's another form of RELU that we can call. So we have a leaky RELU, we have a randomized RELU. If in case the value is not this, then we can start calling it as what? A randomized RELU. Right. So often the range of the leaky RELU is what? It comes out to be what? It comes out to be from your minus to your plus infinity, isn't it? And both the leaky and the randomized ReLU functions are monatomic in nature, and also the derivatives of these functions are also what? Monatomic in nature. Now another variations of these are ReLU functions are, one is called P-ReLU. It gives the neurons the ability to choose what the slope is best in the negative region. So we need to apply some kind of optimization and see that which of the values in the negative region would be the best slope. So they can become a ReLU or a leaky ReLU with certain values of alpha, right? So but that requires some kind of optimization, right? And then we have ELU, that is exponential linear inertia. It leads to a higher classification results as compared to your traditional ReLU, right? And it follows the same rule, like if for x greater than or equal to 0, then it would be the same as ReLU, and it would increase the exponentially for all the values which have x less than 0. So that is where the exponential factor comes into play. Now, ReLU also tries to make the mean derivatives closer to 0, which would definitely increase the speed of the train. If we talk about some of the best practices, that what combination of functions are more used in this as activation functions, then the ReLU is often used in the hidden layer, as I've already told. But we have to be careful with the learning rate, and because the learning rate needs to be monitored so that the training does not become saturate in a lesser number of times. Right? So we have to ensure that the it give enough opportunity to the network to learn, so that the convergence is not achieved in a very quick time. If ReLU is giving some kind of problem, then definitely we should try the other variations of ReLU, that is leaky ReLU or P-ReLU, max out, or we normally do not use a sigmoid function in the hidden layers. And at times it is also suggested that you should normalize your data in order to achieve data variance, in order to achieve better validation accuracy, and so that these standard inputs can also be standardized, right? So once you normalize this data, these ReLU functions or the combination of these functions works much better. The sigmoid or hyperbolic tangent functions cannot be used with where we normally have a number of layers. So normally we in the first layer we often use the sigmoid function or the hyperbolic tangent function, but not in the hidden layers, right? So when we have a higher number of hidden layers, we often push to ReLU function, right? And because since it is suffering from the vanishing gradient problem, the sigmoid hyperbolic functions are not so popular. Another variation, as I have told you in the starting, the softmax function, which is a variation of your this logistic function. Now, the softmax function is nothing but a variation or a type of sigmoid function, but it is handy when we are trying to handle the classification problems, because classification problems, see again, the nature of this softmax function is also non-linear. These softmax functions are used when we are trying to handle what? The multiple classes, because for two class problems, your normal activation functions like logistic function or sigmoid function works pretty well. But when it comes to your multiple classification, multi-class classification, in that case we prefer a softmax function. A softmax function does what? It would squeeze the outputs of each class between the 0 and 1. So at the output layer, we normally use these softmax functions. So for each and every output class, it would convert the values into the range of 0 and 1, and would also divide the sum by the outputs. Because had it been doing only one of the tasks, that is squeezing the value from 0 to 1, it becomes a simple squash function. But we are also doing what? We are dividing that by the sum of the outputs. So that is how, by definition, the softmax function can be defined, right? So the output, the softmax function is idly used in what? The output layer of the classifier, where we are actually trying to attain what? The probabilities of the output of each class. That is what we do in the output class. We determine that what is the probability for this input to belong to which of the output classes. So when we are doing that kind of scenario, then the softmax function is pretty good. So the softmax function is applied only in the output layer, and it is used only when we want the neural network to predict the probability scores during your classification task. Right. So here is a very small comparison between your softmax and sigmoid functions. So in case of softmax functions, which are used for multi-classification, whereas for binary classification, we can always stick to your logistic regression, the sigmoid function. Right. You can work over there. So the probabilities in softmax functions, the probabilities can sum of the sum of the probabilities can be 1, and in sigmoid the probabilities of sum may not be 1, right? And third difference is that the softmax functions, it is used in the different layers of the neural network, whereas but mostly it is used at the output layer, whereas the sigmoid it is used in activation functions while building the neural network. So the output neurons and softmax represent the probability distribution over the mutually exclusive class levels, that you should remember. So like although like if someone asks like which activation function you should go for, so as such there is no thumb rule like which of the activation functions. It all depends upon the way you have trained your network and what function can go fit, or what activation function fits better to your model. So however, we can figure out based on the properties of the problem, right? We might be able to make a better choice of the different efficiencies. So whatever, we'd often try to do a sampling of these functions on a network. And then when we decide like which of the functions are doing pretty good on a sample data, then we can decide upon which activation function would be or has a better possibility of doing well. So this is just a small comparison between the various kind of activation functions, which would help you to give some kind of insight into the activation functions. So I hope you should be able to understand that what all activation functions were used for neural networks. So thank you for this lecture.